Hello everyone, my name is Sasindu Lakshita. Today I am going to explain a very important topic in control system engineering called Nyquist contour and closed loop stability. This topic is help us understand whether a system is stable or unstable before we build in it real life. In this presentation, I will explain everything step by step in simple way. First, we will understand feedback systems. Then we'll learn about the explain, false and zeros. After that, we will learn what the Nyquist contour is and how to draw it. Finally, we will use the Nyquist rule to check stability. So let's start step by step. First, we must understand feedback control. A simple real-world example is a thermostat. Image you set the temperature to 22 degrees. This is called the set point. A sensor measures the actual temperature if the room is cold. Then the heater turns on. If the room is hot, the heater turns off. So the system always compare desired value and actual value. The difference is called the error. This, this error is used to control the system automatically. This loop is called a feedback system, but not all feedback systems behave nicely. Some become unstable. That is why we need stability analysis. Now, why is stability important? If a system is unstable, it can become dangerous. For example, aircraft autopilot system can start shaking. Power system can fail and cause blackouts. Robots can move uncontrollably. uncontrollably. Even medical devices can give wrong outputs. So stability is not just theory. It is very important in real life. To check stability, we use powerful method called the Nyquist stability criterion. The explain now let us understand the explain. In control system, we use SC equals sigma plus j omega. This is a complex number. The horizontal axis is the real part. The vertical axis is the imaginary part. In this plane, we plot poles and zeros. Poles come from denominator. Zeros come from the numerator. Now very important. Left side stable region, right side unstable region. So if a system has poles on the right side, it is unstable. The imaginary axis is the boundary. Understanding this plane is very important for Nyquist analysis. Now let us understand the Nyquist contour. The Nyquist contour is closed path drawn in the S-plane. This path surrounds the right half plane, which is the unstable region. So we are basically checking what happens around the unstable area. The controller has three parts. Go up. First one is go up along the imaginary axis. Second, go around a big semicircle. Third one is come back along the imaginary axis. After drawing this, we apply this transfer function to every point. Now let us see how to draw it clearly. Start at the origin. Go upward to plus j infinity. Then draw a large semicircle on the right side. This semicircle is very big, almost infinite. Then come down to minus j infinity. Finally return to the origin. Now we have a closed loop. Important note. If there is a pole on the imaginary axis, we must avoid it using a small curve. This is called detour. Slides. Next. Uh, Now we map the contour. Take each point and substitute into GS and multiply HS. We get a complex output. Plot all outputs. This gives us Nyquist plot. Now very important. The most important point is minus 1 plus J naught. This is called the critical point. Everything is Nyquist analyzed depending on how the plot behaves around this point. Now the main formula. Z equal n plus p. Let's understand this clearly. Z means number of unstable closed loop poles. N means number of clockwise loops around minus 1. P means number of unstable open loops goal. For stability, Z must be 0. So process is find P, find N and calculate Z. If Z is 0, stable. If Z not equal, it is unstable. This is the core idea of Nyquist analysis. Now let's take an example. GSHS equal to K divided by S bracket S plus 1 and close bracket and S plus 2. First and first poles are 0, minus 1 and minus 2. All are not in right half plane. So P equal to 0. There are no zeros. There is a pole at 0, so we must use a detour. Now we substitute S equal j omega. We get a complex expression. We don't need full calculation, just understand behavior. At omega equal to 0, very large value. At omega equal to infinity goes to 0. So the curve starts far and comes to origin. This helps us to sketch the Nyquist plot. Now look at the plot. We check does it go around minus 1? For small k it does not need any circle. So any circle minus 1. So n equals 0, p equals 0, z equals 0. System is stable. But if k increases, the curve may move and encircle minus 1. Then the system becomes unstable. Now how to count loops. Imagine walking along the curve. Clockwise, positive. Counterclockwise, negative. If no loop n equal to 0, this step must be done carefully. Some special situations. Poles on imaginary axis use detours. Gain margin, how much gain we can increase. Phase margin, how much phase we can lose. Time delay system, harder to analyze. So always be careful with these cases. Is important formulas. Z equal n plus p. S equal j omega. Remember, Z equals 0 is going stable. These are the main ideas you must remember. You accomplish Nyquist analysis procedure. In this slide you can see these steps. First one, find GSHs. Second, find poles, get P. Third one is draw contour. Fourth one, map or Nyquist plot. Fifth, count n. And finally, use formula. Follow this method always. Now we finish. Nyquist contour help us to analyze stability without building the system. We learn contour, mapping, critical point and formula. So Nyquist method is very powerful to in control system. Thank you for watching.